So we spent our time in our previous class talking about the process of optimizing a function of several variables. In other words, just searching for those points at which a function of several variables might achieve its absolute maximum or its absolute minimum value on a predefined region. And we did that in a few steps. The first step is to look for local maximum and local minimum points by finding the critical points of our multivariable function. Those are the places where every directional derivative is equal to 0. And so the first derivative can't show us which direction would be uphill. And then from among all of those critical points, try to classify them. Which ones are local minima, which ones are local maxima, which ones are neither, which ones are saddle points, or possibly something else. And for that, we had a second derivative test where we had to soup up the second derivative by bundling the second order partial derivatives of a function of two variables into a 2 by 2 matrix and using the determinant of that 2 by 2 matrix as a quantity to help us as a stand-in for the second derivative test from single variable calculus. But then that was only a part of the story, right? That only shows us where to look for local minima and local maxima that might also happen to be the absolute minimum and absolute maximum of our function. But if we're doing an optimization problem on a closed region of the domain of definition of our function, a closed and bounded region, rather, of our domain of definition, then the extreme value theorem guarantees that that function will attain a global maximum and a global minimum on that region. But it doesn't tell us that those necessarily need to happen at local minimum or local maximum points, because they could happen on the boundary of that closed region. And so we looked sort of really quickly, unfortunately, at the end of our last class at one strategy that we can use to restrict a function of two variables onto just the boundary of some region. So just some curve, some one-dimensional set of points in the xy plane, for example. And by parameterizing that boundary and then evaluating that function that we're trying to optimize on that parameterization, we came up with a sort of brute force way of turning the question of finding the absolute minimum and maximum of a function on the boundary of a closed and bounded region into a single variable problem that we can just use single variable optimization for. Today we want to do a little bit better than that by coming up with a more efficient, probably, way of finding what are the absolute maximum and minimum values of a function of several variables. For the most part, we're going to be dealing with two variable functions today. When we restrict that function to a curve or a line inside of xy space, so we're no longer going to be thinking about the entire region, filled in region where we might be looking at local minimum and maximum points using the critical points of f the way we started yesterday. Instead, we just want to focus on a sort of one-dimensional subset of the xy plane. And instead of parameterizing that curve or that line or whatever and then doing the brute force way that we did at the end of last class, instead we want to think a little bit smarter about it. And if there is a way for us to describe that curve or that line using a level set equation, so as the set of points for which some other function of x and y is equal to a constant, then that's going to give us a powerful new method to do constrained optimization called the method of Lagrange multipliers. If you talk, I think, to pretty much anybody that uses constrained optimization outside of a multivariable calculus classroom, so if you're using this in science or economics or business or whatever, Lagrange multipliers is 99 times out of 100 the method that they're using, rather than the messy, let's parameterize the boundary and then do the thing that we did at the end of last class. So that's the goal for today, and this is going to take us probably the first third or so of our time together is just to sort of talk through how the method of Lagrange multipliers works.